in time. All right. Are we officially recording?
Yeah.
Oh, good. All right. I'm glad to see you guys were entertained enough by the previous lecture that you want to come out and learn more of what I have to say. So it's kind of our part 2 from the previous series. I remember last time we were talking about this idea of light trapping, mostly in solar cells. And there's all this really cool physics involved and lots of neat cutting-edge research surrounding that idea. And now we're going to talk today about essentially the opposite problem of light extraction. So it's kind of cool that if you get really good at light trapping, it actually makes you very good at light extraction. And if you get good at light extraction, you can be very good at light trapping. At least that's sort of what happened to me. Is my PhD thesis was all about light trapping in solar cells. And then Professor Miller, he owns this company called Terahertz Device Corporation, and they were making infrared LEDs. And he was having this problem of manufacturing these LEDs, but he didn't know anything about the optics involved to get the light out of the LEDs. And he said, hey, I see your thesis is all about getting light into solar cells. Do you think you can work for me and get light out of my LEDs for me? So I said, sure, I'll give it a shot, and worked for him for a couple of years on a lot of various problems related to that. So that's what we're going to talk about here is a lot of the insights I built up and gained in that experience. And, oh, there it goes. So back, forth. There we go. So let's ask ourselves, what is light extraction? So remember this little diagram, just kind of our philosophical introduction to what exactly we're talking about. It's exactly the same diagram. All I did was flip-flop all the arrows in different directions. So instead of light coming from outside and bouncing around and being trapped inside, now I have some magical event here at that little star that's generating light, and it's going to bounce around, and somehow, by hook or by crook or by magic, it's going to get outside of this particular object here. So the natural metric for light extraction is this concept called light extraction efficiency. It makes a nice little acronym, LEE. And it's pretty straightforward. You have all this light energy being generated inside of this thing, and some of it's going to bounce around and be reabsorbed, and some of it's going to leave and get outside, so you just take that ratio. This total energy of light that leaves my thing divided by the energy that was generated inside of it. So if I have 100% perfect light extraction efficiency, then all that energy, all that light that I radiated is going to make it outside. If I have terrible light extraction efficiency, then I'm going to create a bunch of light, create a bunch of photons, and they're all just going to get reabsorbed somehow and turned into heat or other things. Oh, I got a clicker now. Click, click. Your button's a little selective when it wants to. Oh, now it works. Is there a range on it, maybe? So what are some applications for light extraction? I couldn't think of as many really applications for this as I could for the light trapping. We had stealth and anechoic chambers were all about light trapping. In this world, LEDs are really the only place I've seen light extraction really be a thing. So I struggled a little, and sort of a crude sort of alternative is this idea of like antennas, where maybe you have some coaxial transmission line and it goes to an antenna and you're going to radiate light that way. And somehow you have to sort of match the impedances, otherwise you get reflections or absorptions inside the antenna, and rather than radiate that light as actual radio waves. So in a sense, antennas are kind of a light extraction problem if you ever really go down that road. But you're all material science people, you're not RF people, so that's not going to mean a whole lot, I suppose. So really, we're just going to kind of focus on the LED problem. Although I'm kind of curious if there's any other situations where light extraction is kind of an analogous thing. So light-emitting diodes are really where it's at. So why do we like light-emitting diodes? How do they even work? This is kind of fun because my background is mostly electromagnetics, and when I ask that question, most of you here in this room are probably more qualified to answer that than I am. So I'm going to give a little broad overview, and you can tell me if I'm right or wrong. But a light-emitting diode is basically a PN junction, and you run electrical current through it, and electrons and holes recombine in a really super fancy way to make light. And I believe what you want is you need a direct band gap semiconductor rather than indirect band gap, so that that recombination event radiates photons rather than just gets burned up as heat. Is that a pretty reasonable description of a light-emitting diode to you guys? I see some head nodding like, yeah, close enough. So that is about the limit of my understanding there. I never took any of the real material science classes to figure out much beyond that. But probably a lot of you guys are going to make your careers out of this kind of idea. So why are LEDs so amazing and special? So for the last 80 years or so, light bulbs are really the way to make light of varying shapes and colors. Probably more colors than shapes. So how does a light bulb work? You just have some resistor and you run a bunch of current through it and it gets hot, and you run more current, it gets even more hot, and eventually, if you get hot enough, the black body emission spectrum starts spilling over into the visible wavelengths, and your eyes start seeing the light as it comes out of that radiating object. So just by that description alone, you can probably imagine that's a terribly inefficient way to light up a room, right? In retrospect, I probably should have drawn a graph of like a black body radiation spectrum and show, you have that Planck's curve. You're probably all aware of it, but only a tiny little sliver of it is actually contained in the visible spectrum. And I think if you run the numbers, something like 80–90% is way out in the infrared and doesn't actually manifest as anything you can see with your eyeball. So just sort of right off the bat, light bulbs are an inherently terribly inefficient way to light up a room. I think their maximum sort of efficiency at lighting things is something on the order of 10 to 20%, if I'm not mistaken, although I haven't run those numbers specifically. I've seen them before. LED is, however, very special in that you can tune the wavelengths that they emit. If I want a blue LED, I just kind of tune the band gaps just right, and I can get just blue photons coming out. So in principle, they're way more efficient than a light bulb ever could be. And that's why there's been a very big push over the last 10, 20 years to make LEDs kind of the standard for household lighting as opposed to light bulbs. Just their efficiency is much higher, and that can take a large burden off the grid because a big chunk of power that we generate is dedicated just to lighting up our rooms, lighting up our homes. So that's why we're seeing LEDs really kind of slowly but surely replacing light bulbs. I should have added another bullet point here. They're actually a lot more reliable because filaments, when they heat up and cool down, they twist and they bend and they wear out, and you only get so many hours of operation out of the things. So, they're cheap, but you have to replace them all the time. And that can be frustrating and kind of have an inherent cost that you may not like. So LEDs are nice that they don't really have any bending, moving parts. They're kind of this solid state thing. They don't heat up and cool down and twist and bend the way the filament does, so they last a lot longer. I think the typical life expectancy on an LED is probably something like 10, 20 years at least. I see some head nodding. That sounds about right. So me personally, every time a light bulb goes out in my house, I am slowly but surely replacing them all with LEDs, and then I'll never have to replace a bulb again, or at least not before I sell the house and go somewhere else. So, there's a lot of motivation to use LEDs everywhere. Even if they're slightly more expensive, just that convenience can be nice. Another really cool thing about LEDs is you can modulate them very, very quickly. So let's do a quickie experiment here. I'm going to modulate the lights in this room. You notice they don't turn on and off very quickly, right? So how many bits per second do you think I could send through a channel if that was my light source there? So let's just see how long it takes to turn on. And on, off, on, off. So I can send about a bit per second with that, right? My slide jumped. I guess I have to get really close here. Okay. So LEDs, really, they're a bit faster than that. Light bulbs are limited essentially by how fast can they heat up and cool off, and that means you're kind of stuck in the heat equation, and there's only so much speed you can turn on and off an incandescent light bulb. And you're just limited by the fact that the atoms have to heat up, and then they have to cool down and heat up again, and that's how many bits per second you can send. And even under very ideal conditions, the best you can get is maybe, I don't know, 100 hertz tops, if I had to guess. Not a whole lot. You know, you're limited to milliseconds, many milliseconds in rise time and fall time. LEDs, however, even a cheap, crappy one can easily be microseconds of rise time and fall time. And I think you're kind of inherently limited by the internal capacitance of the LED for that sort of thing. But in principle, they can get very, very fast. A lot of the LEDs we worked on when I was doing the infrared LEDs, you know, a 1 to 2 microsecond rise time was easy, and that was without even really trying to make them fast. So right out of the gate, they're at the megabits per second kind of threshold, just by the simple virtue that you can turn them on and off very quickly, so I can send lots and lots of bits per second. Another really great thing about LEDs is they're actually surprisingly cheap to manufacture. So if we go back one slide, let's go here. Come on. There we go. So those are like some little off-the-shelf LEDs you can get from Radio Shack or somewhere. Here's a fun question. How much area do you think the little semiconductor die is in that LED? There's a little tiny chip in there, the semiconductor, that when you run current through it, it glows. How much volume do you think that little chip takes up? Because the rest of it is just this sort of colored epoxy to protect it. Throw out a guess. Less than a millimeter? Well, I'll give you a hint. When we did our infrared LEDs, they were 1 millimeter by 1 millimeter square. The whole thing? The whole chip, yeah. And that was considered big. Okay? So, what do you think this guy is here? A square micron? I hear a square micron. You think that's small or large? That's actually probably pretty small, the square micron. I believe I've heard legends that they're typically on the order of about 100 microns by 100 microns square. Okay, so about 1/10 of a millimeter is pretty common for a chip size in these things. So remember, when you make these at a semiconductor fab, you have a wafer that's maybe 6 inches or so, about the size of your hands in a little ring here. And you might process like 5 of these at a time, and that little batch would probably cost you somewhere around $50,000 to $100,000 to process that batch. But how many chips do you think you can get out of 5 wafers that are about 6 inches in diameter? If the average chip size is 1/10 of a millimeter or so. So if you just run the math order of magnitude in your head, how many die do you think would come out of that? 10,000, 100,000, a million? Head nods. It depends kind of how efficiently you pack them in there. Oh, you're going to give a guess? Lots? A gajillion? So it kind of depends on how tightly you can pack them in, because you do have to kind of run a little buzz saw through to chop them out. Or there's probably fancy ways to cut that. I know in some processes that you cut a little square and you need a little space where the saw will physically go in and cut them apart. But, 6 inches or so, you can pack many tens of thousands of chips on that in principle. And then when you do like a batch of 5 of them together, there's more tens of thousands. So you can easily get somewhere like a couple 100,000 chips off of a single process run. And that process might cost you somewhere between $50,000 to $100,000 to run. But if I get multiple hundreds of thousands, then you're really like 10 cents per die or less is not unheard of. And I think if you buy these guys off the shelf, how much do you think this little red LED costs if you to go to Radio Shack and buy one now? 50 cents, 20 cents? So that chip there is easily below, 20 cents a piece. Yeah. So they're ridiculously cheap to make these things. There are limitations, of course, because a smaller little die doesn't necessarily mean you can get as much brightness or much total radiated power out of the thing. So, if I had twice the area, I would be emitting twice the photons, and it would look twice as bright in principle. But, that's kind of a whole other discussion on how to make these things bright enough to fill a room. But the long story short is we really like LEDs. They're pretty cheap. They're straightforward to manufacture. They modulate, they're efficient. There's all sorts of good things about LEDs. There is, however, one nagging problem that gets in the way of good LED efficiency. Well, I shouldn't say there's one nag. There's lots of problems, but today we're going to focus on this one. And this is the problem of light extraction. Because, yeah, somewhere in here you imagine a semiconductor, and there's an electron and a hole. They wander in, they recombine, they create a photon, but that photon still needs to get out of the semiconductor. And you might be aware of a little pesky thing called Snell's law, right? So normally it just makes refraction at surfaces a big deal, but when you start from inside a dielectric and you need to get out into air, you have this problem of total internal reflection. And I say problem for us because if you're doing fiber optics, that's what you rely on for your bread and butter. But in this context, it's terrible because it means only a handful of your photons are going to fall into that little escape cone. And any other photon, if it's outside, it just ricochets off the boundary here and travels back down and probably gets reabsorbed and turned into heat. So that's bad. You need some way to get those photons out of the semiconductor or else they're not going to do you any good. So this diagram here on the right is really cool. This represents kind of a full wave solution to this ray approximation here. So I just think it's really cool. I spent like weeks kind of solving this a long time ago, so I'm showing it off. But it's the exact same thing from kind of a 2D electromagnetic Maxwell's equations kind of perspective. So here's the boundary right here. And right here is a little current source kind of wiggling back and forth, and it's radiating an electromagnetic wave in all directions. So you have all these rays going down, and there's some up here. And right about here, you see is the escape cone. And that's where this little wave here is kind of escaping out. But there's all these reflections coming down. So we kind of go back and forth a little between kind of the full wave perspective, and then there's kind of the ray optics perspective, and then the quantum perspective. And so if one moment I'm talking about electromagnetic waves, and then the next moment I'm talking about photons, just remember they're kind of actually the same thing when you think about it. So I hope that's not confusing. But there's advantages and disadvantages to kind of looking at the system from different physical perspectives. Obviously, the ray optics is kind of simple and intuitive and straightforward. The full wave perspective is great, but really, that isn't really what's happening. There's photons bouncing around, and that wave represents really the probability of finding the photons. Just kind of keep all that in the back of your mind. It's all the same thing, really, in different words and different perspectives, but mostly it's different mathematical complexities that you're worried about. So, this is a funny thing about light extraction is everyone's sort of aware of it, but when you really try and study the problem, not a whole lot of people have really formalized it. So I actually got a couple of papers out on this where I took kind of the textbook treatment of it and expanded on it as someone with a strong background in electromagnetics and did a lot of the calculus and the Maxwell solutions, everything, and got some nice, cool results out of it. And they're pretty neat from an academic sense. They give you a lot of intuition about what's going on, even though there may not be the most immediate practical applications for what we're doing or what we're going to talk about. But they are good for kind of getting a good, solid mathematical intuition of how everything works. So this is a nice model of the quintessential light extraction problem, where you imagine an electron and a hole wander around and they recombine here. So that little red arrow represents this little instantaneous brief moment where there's a current density. And you can think of that as if I have an electron and I have a hole. Those are positive and negative charges in space. And when they have some spatial distribution, and when they recombine, that charge density physically rearranges itself in space. So from the perspective of Maxwell's equations, that would be modeled as kind of this blob of current density. So if I have current density, a changing current in time, not just a constant current, but a changing current, that gives rise to electromagnetic waves. That is how photons are created. Is you take charges and you smush them and wiggle them, and that will create photons. So that little J vector there represents the current density, and it has a direction too, because the direction is important in how it will radiate light. So you look at the inset here, it's kind of a zoom in. You imagine a little surface around it, and what I'm going to do is integrate the flux across that surface. So what I mean by flux specifically, it is called the Poynting vector. If you take optics, you probably will call it like a radiant intensity, I think is the word. No, flux is just the word from optics. But in E&M, it's really called a power density, and it's kind of this cross product for the electric and magnetic fields. And but at the end of the day, all you need to know is it represents power density, watts per square meter of energy being spewed out from that little current density. So if I integrate a surface around it, it's watts per square meter integrated around a surface just gives me watts. There's some power being radiated by that little event. Or if it's an event over a short time, I could just kind of analogously say there's some total energy that was radiated by that event. And you can calculate it just by integrating around that little dipole there. So that tells me this integral here, so you notice this omega is that surface, and I'm just integrating that little surface to get a total radiated power. And that is the denominator in my light extraction efficiency, total power generated. Those are all the photon energy that was created in this event. So we'll go next. Okay. So what happens is you imagine a electromagnetic wave just kind of radiates out in every which way. And that contains sort of the probability of what the photons are going to do. So they're kind of analogous ideas. And some distance away, there's a boundary between this dielectric and air. And because the dielectric, oh, you're checking. So the dielectric is, we say it's more dense, meaning that the dielectric constant is greater, or the index of refraction equivalently is greater. And so region 2 is typically, it can be anything you want, but most often it's just air, because that's the world we want the light to get out into. So, I've got a muse and epsilon, but they're usually non-magnetic, so I'm kind of overkilling the notation here. But as the most common simple case, you can say there's a dielectric constant here, or an index of refraction, and then up there is just air. So it would be mu and epsilon are 1, the relative permeability and permittivity. Now, from Snell's law, there's this escape cone. So some energy is going to kind of fall outside and reflect back down, or some energy is going to fall in the escape cone and escape out. That's kind of the simple case for a flat planar boundary. However, in principle, it doesn't have to be perfectly flat. It could be like some roughened surface texture, or I could put some diffraction grating or whatever up there. And that would completely scramble this escape cone. So if I wanted to know how much energy is escaping, I could, in principle, just integrate all the flux that leaves this top surface. And that's what this integral here represents. It is the integral of all the power that leaves that top surface at z equals a, technically. So you see it, we're integrating along x and y, so that's coming out and parallel to the plane here. And a is this z equals a point. So all the flux that just leaves that surface is all the light that was extracted. Then if you divide by that total radiated power, you have a light extraction efficiency. Okay, that's pretty intuitive so far. I'm talking a lot, but not really saying too much, I hope. So with that mathematical definition in place, you can actually do some very straightforward calculations to give yourself a sense of how bad this problem is. So a very simple calculation is to say, let's imagine light is radiated equally in all directions, which isn't exactly true specifically when an electron and a hole recombine, but in some cases you can treat it that way. So we call it isotropic radiation. Isotropic means like same in all directions. So it doesn't matter if I'm down here or up here or over that way, it's radiating equally in all directions. And then I'm just going to calculate how much energy gets into that escape cone. And for simplicity, you can even imagine, let's suppose there's an anti-reflection coating on top, which will completely eliminate any reflections within the escape cone. So a fun fact, anti-reflection coatings, they can eliminate all the reflection in the escape cone, but outside, there's nothing you can do. So it's called anti-reflective, but not, it actually can't be perfect in that sense. You can actually kind of prove from Maxwell's equations that no matter what I kind of do above this plane, I will never escape the escape cone. See what I did there? It'll always kind of be there. If you roughen it and make it bumpy, that's different. But with the planar structure here, you can't you can't get rid of those reflections outside of the escape cone. So just kind of think about that. But I can actually minimize them very well inside the escape cone. So for all practical purposes, we'll say, let's suppose it's absolutely perfect in the escape cone, and outside everything reflects through total internal reflection. So the total light extraction efficiency is actually just the ratio of the solid angle in this little cone divided by the total solid angle, which when you run the numbers, you get this 1 minus cosine theta c kind of term over 2. So I think the over 2 is, I believe that just stems from the fact that all the energy that goes down is going to be trapped forever. So there's no bottom boundary. So that limits you to 50%, I believe. So the escape cone from Snell's law is just here, and you run the numbers. So what's a typical index of refraction for a semiconductor now? That's the big question. And the answer is, if you look at like gallium arsenide, gallium antimonide, and indium arsenide, all these guys, typically they have an index of refraction that's somewhere between 3 and 4-ish. So somewhere around 3.5 is pretty typical. So you put that number into Snell's law to get my escape cone, and you find that it's usually about 15 degrees. So that calculation, finally, I get a light extraction efficiency, and I get 1.7%. It is about the best I could do if I were to just leave everything alone. So that should ring a few bells. That's obviously very terrible, right? So you can see kind of the scope of the problem for light extraction in an LED. If you can make the most absolutely perfect, internally quantum efficient LED in the entire universe, but if you just don't treat the surface in any special way, you will absolutely never get above 2% efficiency. All the rest of your energy is just going to be trapped inside and reabsorbed and never seen again. So that raises some questions. How can we make that better? Because that's obviously terrible. That's less than 1 in 20 photons are going to get out. All right, so let's kind of change up the math a little bit. So this idea of a perfect isotropic radiator is actually not what happens in real life. So if you imagine, say, an electron and a hole recombine, and there's a brief moment where there's a current density and it's sort of oriented this way, up and down, it would actually preferentially radiate all my light sideways. So you can see right off the bat, that actually can make things a lot worse, because if we go back one slide, beep, so very little energy might actually radiate up. Instead, I'm just going to radiate this way, which is going to really hurt my efficiency even more. So this is a problem I haven't seen a whole lot of literature on. I've seen a few people kind of dabble that there is some kind of inherent polarization inside LEDs, but I've never really seen anyone kind of tackle what is the polarization of that electron-hole recombination event. Is it up, down, or is it left, right? Because that actually has a big impact on your light extraction efficiency. So this is a pretty straightforward, well-known model. If you treat that event as if it's very tiny and very small and very brief, you can call that a Hertzian dipole. It just means a short dipole, a tiny little infinitesimal point of current that exists for a moment. And what will happen is, because there's a direction, it has this thing called directionality, which just is a measure of how preferentially does it radiate energy in one direction over another. So this is a well-known thing. If you ever take advanced E&M kind of classes, you'll run into this guy. And there's a big 9-page derivation where you find that the directionality is represented as this sine squared dependence. So that means is no energy is going at 90 degrees, and most of your energy goes at 0. Wait, sorry, that's backwards. So what's theta here? So this is a polar theta, I think. I believe theta should be, that way. So this should be 90. So this is 0, and that's 90 degrees that way. Okay. So just make sure we have our 0 reference correct. Okay. That wasn't confusing, was it? The long story short is there's directionality in how things radiate. So what you can do now, so I actually have a paper that's in Optics Express that kind of goes through all this derivation. And it's pretty straightforward stuff, just a lot of heavy-duty vector calculus. What you do is you convert this rectangular integral to kind of a polar coordinate. And this G term represents kind of the directionality of where energy is being radiated by your little source. and then you're integrating over polar coordinates, and this T represents your transmittance kind of through that boundary when a photon hits in that direction. So if you just integrate all the photons and where they're going preferentially and how many of them get through the barrier, you have this nice closed form expression for light extraction efficiency. It looks horrible, but it's actually pretty tractable. You sit down, you can crunch it using little more than some calculus and third semester calculus. So for example, you imagine the Hertzian dipole, that G term is this sine squared there, and I'm kind of skipping the derivation. We're imagining the transmittance is perfect through the escape cone, and then 0 as you go out and beyond it. So that, is just a pretty straightforward piecewise integral you can do. And the whole thing gives you this nice closed form solution. So you can kind of calculate in advance what is the absolute best light extraction efficiency I can expect, assuming my recombination event has some preferential direction to it. And then you can say, well, what if it's actually the other way? Because that could work for you rather than against you, right? If by some fluke, the p-n junction and all the band gaps are arranged in such a way that when those electrons and holes recombine, they preferentially have a current that's horizontal instead of vertical, you can get more energy to come out through that escape cone rather than less. So that's something I've never really seen people do deliberately, but it is a thought in the back of your mind that it is there and can be accounted for. So you get another closed form solution, and that's fine. And this is really kind of what they look like at the end of the day. So this is a really cool graph showing light extraction efficiency as a function of the critical angle on the bottom graph, or equivalently on the top we have the index of refraction. So as the index approaches infinity, your critical angle goes to 0. And as your index goes to 1, which is space, your critical angle is 90 degrees. So it's actually 90, and then you spin around to make that cone, essentially. That makes sense. So in other words, you see your light extraction efficiency approaches 50% in the event that your index of refraction goes to 1. That's because all the photons that went up are just going to get out without any reflection, but all the ones that went down are being reabsorbed. So we're kind of assuming that there's no mirror in your back contact. However, what I could do is put a mirror at the back, and all that means is all the energy that went down is just going to bounce back up again, kind of at the same angles from, again, Snell's laws. And so all you do is kind of multiply everything by 2 if that happens. So the general assumption is like this infinite half space with a little boundary on top. So that's why we have 50% here. And if you really want to get motivated, you can have anti-reflective coating, or you can account for what's called Fresnel reflection. And that's if you just have this planar boundary between two dielectrics. You don't just get transmission, you also get reflection, and you can kind of account for that too. So there's 3 curves here technically, and each curve is kind of a little doublet. And what you're just seeing is, say, here's the parallel. You see how it's kind of the biggest of the bunch because I'm orienting energy into the escape cone. The perpendicular is obviously the worst of the bunch because very little energy is actually going up into the cone. And then in between there's this isotropic because sometimes maybe one recombination event will be this way and then another one will be that way. And in principle, if you statistically average millions and millions of recombination events and they're all randomly oriented, it does actually converge onto the isotropic approximation. So it's not that any particular thing in the world will be isotropic, but statistically they can behave that way. So it's useful to kind of put that in there as well. So what do we learn from this graph? So again, the typical semiconductors are anywhere between 3, 2.5 to 4 in their index of refraction. So that means from about here at 30 degrees to here around 15 or so, this is where most semiconductors in the real world tend to fall. And what you find is, okay, I can maybe get 10%, but really most of the time I'm around this kind of 5-ish% at best, and that's being kind of generous. Okay. Another fun graph is, what if I still have that planar boundary, but I put a mirror at the back and I roughen it? Now I have Lambertian scattering. So now all those rays are going to escape out in this sort of cosine theta dependence. And it's neat, you get this nice closed form sine squared curve, for the black curve. But it actually goes to 100% now because we have this kind of mirror at the back. So there's no energy going down, it's all just going up. So that's just a sort of a fourth calculation you can throw at it and learn interesting things about. So this is just kind of a zoom in of all the curves that matter. So you find critical angle, I'm only going from 0 to 25 instead of all the way to 90. And you're zooming in, typically around 15 degrees. Okay, if I have Lambertian scattering at the back, I can get about 4 or 5%. If they're all oriented in the wrong direction, the perpendicular, you notice I get like less than 1/10% of light extraction. If they're nicely oriented, I can get up to 2, 3%, and then the isotropics again about 2-ish, 1 to 2%. So again, this is all just to kind of show that even under all these various conditions of orientation for the dipole, unless I really do something to that top surface, I'm not going to get more than 5% light extraction efficiency. So there's a lot of room to do better here. So at the end of the day, what you usually will probably see is something maybe like this, where you make the top surface bumpy. So now it doesn't really matter which direction you come in and hit it from. There's no distinct escape cone anymore. There's just some probability of the photon either getting out or it'll reflect and rescatter and then bounce off the back and then reflect again. So if I have a finitely thick semiconductor here, I can, in principle, get a lot more light extraction simply by just having rays bounce around a lot back and forth and hit the surface many times over. So this was an analysis I did and got a nice conference publication out of it. And this idea is, when you make things bumpy, everything's going to kind of become diffuse or Lambertian. So we can kind of use that as a general limiting case for lots and lots of bounces. And we'll just do kind of that analysis we did in last Tuesday, where you remember with the Yablonovich limit, we just tracked rays as they bounced up and down a bunch of times, and then kind of got that infinite series idea. And we're going to do the same thing, only now instead of calculating how much power is absorbed inside of this thing, I want to know how much power is getting up. So it's like really the same math, you're just sort of solving for different terms. And all I got to do is remember that technically this is a lossy material here. There might be some p-n junction here where all the action is occurring, but there's going to be some bulk material that's going to reabsorb photons and convert them to heat. Although I have been told if a photon gets reabsorbed in that p-n junction in just the right way, it can actually just re-excite an electron a hole again, which will then wander around and recombine and create yet another photon, and I believe people have kind of dabbled in that to try and make their LEDs more efficient. Because the idea is instead of losing that energy to heat, you're just kind of creating a new opportunity to re-radiate a photon and get it back out again. I don't know how successful that's been, but I do know that idea is on people's minds, and they've dabbled with it in the literature. So from what follows now is a very similar calculation. You just do these little integrals in polar coordinates, and you're just tracking rays as they bounce around inside of the LED. And these are some curves that you can do to calculate the absorption as it goes up and down in a bounce or two, and versus the thickness of your slab. So obviously you can see this neat little trend where if my slab is really, really thick, it doesn't matter really what I do because I'm just going to lose all that energy that bounces down and gets reabsorbed. But as I make my slab really, really thin, then I get lots of bouncing and bouncing between the back and front contact with very little absorption in between the bounces. So fun fact, the attenuation constant for various semiconductors varies wildly. So these are just some kind of curves that you find when you run this calculation. So obviously, a very low attenuation means I can have a very thick slab before I have any serious absorption here. And obviously, a very high attenuation means I need a very, very thin slab, say less than a micron, or else I'll lose half my power in each little bounce here. So I believe most semiconductors kind of fall in between here, where you need somewhere between less than 10 but more than 1 micron or so to get to avoid serious attenuation. So right off the bat, you can see, okay, if I need two things really if I want to minimize absorption or reabsorption inside my LED. I need it to be very thin, otherwise I lose all the energy in the back and forth propagation. And I would like it to be a low loss or low conductivity material inherently. So some LEDs and some semiconductors are going to be kind of better at this than others, and it's just going to depend on what you have control over and what you don't. So then what you do is you ask, okay, some light bounces from top to bottom, and when it hits that top surface, how much of it is going to escape out there into the external world? And this is a really important idea. So some little fraction, maybe like 2% of the energy is going to escape, and then it's going to re-radiate down and back, and then another 2% of that will escape, while another couple percent gets absorbed, and then you just kind of do this infinite series calculation and just adding up absorption, emission with each of these little bounces. And they're tractable. They're these kind of these big, ugly integrals, but if you can calculate that integral, you can generate the infinite series and see where it converges to. So just kind of skipping to the result, you see something that kind of looks like this. So this is the extraction factor, that eta. That's how much energy emits into the external world when the light hits that top surface. And the A represents how much is absorbed as it bounces back and forth between each of those escaping events you can think of. So obviously, if my absorption goes to 0, I get light extraction efficiency of 1. And if my absorption gets very, very high, I get very low light extraction efficiency. It can never quite be 0 because you always get at least that first opportunity to bounce out the top. So you get this infinite series, and so these are some calculations I did, and I threw them in, put them up in a conference publication once. But the general take-home point is you have a very thick slab, your light extraction efficiency is stuck here at like 5-ish%. But as I make it very thin, I get lots and lots of opportunity to bounce around, and very, very thin, you can even shoot up to almost 100% light extraction efficiency. So I believe it's not unheard of using these kinds of techniques to easily get up to around 80-ish, 90-ish% on your light extraction efficiency. You're never going to quite get to 100, but it can be done using, just clever engineering. So let's look at some parallels. So remember last time we talked about light trapping, then we did light extraction, and they're like the same, but they're different. So light trapping, the idea is let's get light into a semiconductor, at least with solar cells, that's the idea. Then you have LEDs, and the idea is completely backwards. I'm creating light, and I want to get it out. So in both instances, we find that having an anti-reflection coating actually makes everything better because reflections just mean light either bounces way back into space or gets rebounced back into your semiconductor. And both of those situations are bad in both cases. So anti-reflection coatings are good in both cases, whether you're doing light trapping or light extraction. So in light trapping, we found attenuation is good. I want my solar cell to absorb as much light as I possibly can in each bounce. When I do light extraction, attenuation is my enemy. I don't want any energy to be absorbed in that bounce. I want it to stay free so that it gets out into space when it hits the top surface. So light trapping, we found, okay, thick films are good. The thicker I can go, the more energy I can absorb. And that was our enemy, though, because thick meant money. It was costly to do that. In light extraction, thin is now it. We want to be as thin as we possibly can, so we get as many bounces as we can get out of it. And again, there's only so thin you can go before the thing is like physically, mechanically unable to even like support itself. But people have probably thought about that and found ways to really get around that problem. And then in both cases, we found surface roughening absolutely, totally helps. Rough is good. Flat, planar surfaces, as a general rule, are pretty bad, and we don't like them. Okay, so it's neat how some design principles stay the same, but others just completely trade places. So last time we did kind of a thought experiment. So this is a fun one to think about. This is one of those little geometries that when you look at it, mathematically and physically, you're like, yeah, that's absolutely perfect light extraction. If I have a little recombination event at the exact center of a sphere, and I coat it with an anti-reflective coating, there's no more escape cone I have to worry about because all angles are going to be perfectly normal to the surface. So I can get perfect light extraction with this geometry, right? So now this is again one of those instances where you're going to pretend I'm your pointy-haired boss, and I come to you one day and I say, why aren't we doing this? This will work perfectly. Is this a good idea or a bad idea? I'll let you think about it for a second. So, I don't know, let's start with like the obvious question is, where exactly is the PN junction going to go? You need current to flow from a P to the N, so somewhere you need contacts, and a PN junction in there has to, how do I get a PN junction inside a sphere like that? I honestly don't know. You're the material science people who spend a lot more time in the nanofab than I do. Is that even doable? I see a lot of skeptical looks. Oh, sure, okay, yeah, okay. So where would the PN junction go? Could it go over here on the left or here? Does it have to be in the center? What if it was kind of over here to the left some? Or maybe a big plane that cut down the middle? What would happen to a photon that's emitted here? Well, you know, if it's here, I have an escape cone kind of off to the left. But what about over in this direction if I follow a ray? Am I going to be in the escape cone or not? Probably not, because you can see I have a steep angle I have to now hit this surface with. But I don't know, maybe I'll just kind of reflect out and hit an escape cone somewhere else. Maybe that's not too bad. But the big question is, when I look at this, I think, where exactly are you going to put the junction? How do you get the junction in there? Where are the surface contacts going to go? What happens when some photons are emitted not in the middle, but off to the side somewhere? They inevitably will be. And really, how do you make it? Because all the semiconductor processes I've seen are very planar. They like big, flat, planar rectangle surfaces. And if I come to you with just, you know, a little sphere of gallium arsenide or indium phosphide or something, I say, here, make me a blue LED out of this. Like, I don't know, would you even know how to do that? Could it be done? Maybe. And what if I told you that all you had to do was actually maybe something like this, make it 5 microns thick and make it bumpy on the surface, and you're going to get 80% light extraction anyway. And we know how to make that. We know our systems are happy with little planar bits like that. And if I go back to the circle sphere here, I don't even know how to begin with that. So again, this is one of those great ideas where it sort of seems great. You're solving all your problems. I get perfect light extraction. But then you're like left with this weird question of, I don't even know how to make that, or don't even know where to begin. And even if it did work, the best I could do is 100%. Whereas if I know I have this other thing that probably will give me 80%, so would you rather have an 80% that you're pretty sure you can get, or spend 10 times as much money per die to get 100%? I don't know, is that even worth it to you? Maybe you do care about that little 20%. Or maybe in practice, this will only maybe give you 85% rather than 80, because it won't be absolutely perfect. You can't concentrate everything at the center of that sphere. You have to spread something out maybe. So maybe in principle you can get 100, but practically when you try it you get 85 or 70 for all you know, right? So it's just fun to think about, because I actually had this kind of exact discussion with my own boss when we were making our infrared LEDs. It's like, well, could we do something like this? I'm the EM guy. You're the semiconductor guy. You tell me. So anyway, are there any questions on that? That's the end of our discussion today. A little shorter than last time. You feel like you're all experts in light extraction. I've got a couple of citations you can read if you really want to read further. But if we go back a few slides here, you know, these graphs here, this was actually a paper I did in Optics Express, where I did all these kind of calculations just to show what happens when you get directional sources inside of an LED and how good can you do, really. And then this bunch of calculations here was kind of a conference paper I did as a follow-up, just showing, okay, you make it bumpy, and here's some math you can throw at it and get real interesting results out. So it's stuff people are sort of aware of, they dabble in it, But I really think a lot of the situation is kind of like this room right here. Most people who do LEDs and solar cells are like semiconductor people, material scientists like you guys, and very few electromagnetic people get involved in it to tell them how the optics are really should be optimized. So it's the sort of thing where they sort of know it. I mean, they've taken the physics classes here and there, and they're aware of these problems, but they don't necessarily have that kind of mathematical experience or background to really formalize it. So it's kind of neat to be the outsider in these kinds of problems because it gave me some opportunity to formalize a little bit of their work here. Okay, so like I said, any more questions, or you all feel enlightened now from that, from having experienced that? Okay, well then, thank you for coming out.